The goal of DSPs is usually to measure, filter and/or compress continuous real-world analog signals. Most general-purpose microprocessors can also execute digital signal processing algorithms successfully, but dedicated DSPs usually have better power efficiency, thus they are more suitable in portable devices such as mobile phones because of power consumption constraints. DSPs often use special memory architectures that are able to fetch multiple data and/or instructions at the same time. Overview. Digital signal processing algorithms typically require a large number of mathematical operations to be performed quickly and repeatedly on a series of data samples. Signals are constantly converted from analog to digital, manipulated digitally, and then converted back to analog form. Many DSP applications have constraints on latency, that is, for the system to work, the DSP operation must be completed within some fixed time, and deferred processing is not viable. Most general-purpose microprocessors and operating systems can execute DSP algorithms successfully, but are not suitable for use in portable devices such as mobile phones and PDAs because of power efficiency constraints. A specialized digital signal processor, however, will tend to provide a lower-cost solution, with better performance, lower latency, and no requirements for specialized cooling or large batteries. The architecture of a digital signal processor is optimized specifically for digital signal processing. Most also support some of the features as an applications processor or microcontroller, since signal processing is rarely the only task of a system. Some useful features for optimizing DSP algorithms are outlined below. Architecture. Software architecture. By the standards of general-purpose processors, DSP instruction sets are often highly irregular. One implication for software architecture is that hand-optimized assembly code routines are commonly packaged into libraries for reuse, instead of relying on advanced compiler technologies to handle essential algorithms. Instruction sets multiply accumulates operations used extensively in all kinds of matrix operations, convolution for filtering, dot products, polynomial evaluation. Fundamental DSP algorithms depend heavily on multiply accumulate performance for filters, fast Fourier transform instructions to increase parallelism, SIMD-VLIW superscalar architecture, specialized instructions for modulo addressing and ring buffers and bit reversed addressing mode for EFFT cross-referencing. Digital signal processors sometimes use time-stationary encoding to simplify hardware and increase coding efficiency. Multiple arithmetic units may require memory architectures to support several accesses per instruction cycle. Special loop controls, such as architectural support for executing a few instruction words in a very tight loop without overhead for instruction fetches or exit testing. Data instructions saturation arithmetic, in which operations that produce overflows will accumulate at the maximum values that the register can hold rather than wrapping around. Sometimes various sticky bits operation modes are available. Fixed-point arithmetic is often used to speed up arithmetic processing. Single-cycle operations to increase the benefits of pipelining. Program flow floating-point unit integrated directly into the data path. Pipelined architecture. Highly parallel multiplier accumulators. Hardware-controlled looping, to reduce or eliminate the overhead required for looping operations. Hardware architecture. Memory architecture. DSPs are usually optimized for streaming data and use special memory architectures that are able to fetch multiple data and/or instructions at the same time, such as the Harvard architecture or modified von Neumann architecture, which use separate program and data memories. DSPs can sometimes rely on supporting code to know about cache hierarchies and the associated delays. This is a trade-off that allows for better performance. In addition, extensive use of DMA is employed. Addressing and virtual memory DSPs frequently use multitasking operating systems, but have no support for virtual memory or memory protection. Operating systems that use virtual memory require more time for context switching among processes, which increases latency. Hardware modulo addressing allows circular buffers to be implemented without having to test for wrapping. Bit reversed addressing, a special addressing mode useful for calculating FFTs. Exclusion of a memory management unit. Memory address calculation unit. History. Prior to the advent of standalone DSP chips discussed below, most DSP applications were implemented using bit slice processors. The AMD 2901 bit slice chip with its family of components was a very popular choice. There were reference designs from AMD, but very often the specifics of a particular design were application-specific. These bit slice architectures would sometimes include a peripheral multiplier chip. Examples of these multipliers were a series from TRW including the TDC1008 and TDC1010, some of which included an accumulator, providing the requisite multiply-accumulate function. In 1976, Richard Wiggins proposed the speak and spell concept to Paul Breedlove, Larry Brantingham, and Gene France at Texas Instruments' Dallas Research Facility. 2 years later, in 1978, they produced the first speak and spell, with the technological centerpiece being the TMS-5100, the industry's first digital signal processor. It also set other milestones, being the first chip to use linear predictive coding to perform speech synthesis. In 1978, Intel released the 2920 as an analog signal processor. It had an on-chip ADC DAC with an internal signal processor, but it didn't have a hardware multiplier and was not successful in the market. In 1979, AMI released the S2811. It was designed as a microprocessor peripheral, and it had to be initialized by the host. The S2811 was likewise not successful in the market. In 1980, the first standalone, complete DSPs, the NEC Micro PD7720 and AT&T DSP-1 were presented at the International Solid-State Circuits Conference, AT. Both processors were inspired by the research in PSTN telecommunications. The Altamira DX1 was another early DSP, utilizing quad-integer pipelines with delayed branches and branch prediction. Another DSP produced by Texas Instruments, the TMS-32010 presented in 1983, proved to be an even bigger success. It was based on the Harvard architecture, and so had separate instruction and data memory. It already had a special instruction set, with instructions like load and accumulate or multiply and accumulate. It could work on 16-bit numbers and needed 390 nanoseconds for a multiply-add operation. T is now the market leader in general-purpose DSPs. About 5 years later, the second generation of DSPs began to spread. They had 3 memories for storing 2 operands simultaneously and included hardware to accelerate tight loops. They also had an addressing unit capable of loop addressing. Some of them operated on 24-bit variables, and a typical model only required about 21 nanoseconds for a Mac. Members of this generation were, for example, the AT&T DSP-16A or the Motorola 56000. The main improvement in the third generation was the appearance of application-specific units and instructions in the data path, or sometimes as coprocessors. Some chips, like the Motorola MC68356, even included more than one processor core to work in parallel. Other DSPs from 1995 are the TTMS-320C541 or the TMS-320C80. The fourth generation is best characterized by the changes in the instruction set and the instruction encoding, decoding. SIMD extensions were added, VLIW and the superscalar architecture appeared. As always, the clock speeds have increased. A 3 nanoseconds MAC now became possible. Modern DSPs. Modern signal processors yield greater performance. This is due in part to both technological and architectural advancements like lower design rules, fast access to level cache, DMA circuitry and a wider bus system. Not all DSPs provide the same speed and many kinds of signal processors exist, each one of them being better suited for a specific task. Ranging in price from about $1.50 to $300, Texas Instruments produces the C6000 series DSPs, which have clock speeds of 1.2 GHz and implement separate instruction and data caches. They also have a second-level cache and 64 EDMA channels. The top models are capable of as many as 8,000 MIPS, use VLIW, perform 8 operations per clock cycle and are compatible with a broad range of external peripherals and various buses. TMS320C6474 chips each have 3 such DSPs, and the newest generation C6000 chips support floating point as well as fixed point processing. Freescale produces a multi-core DSP family, the MSC81XX. The MSC81XX is based on Star-core architecture processors, and the latest MSC8144 DSP combines 4 programmable SC3400 Star-core DSP cores. Each SC3400 Star-core DSP core has a clock speed of 1 GHz. The processors have a multi-threaded architecture that allows up to 8 real-time threads per core, meaning that a 4-core device would support up to 32 real-time threads. Threads communicate between each other with buffered channels that are capable of up to 80 Mbit per second. The devices are easily programmable in C and aim at bridging the gap between conventional microcontrollers and FPGAs. CEVA, Inc. produces and licenses 3 distinct families of DSPs. Perhaps the best known and most widely deployed is the CEVA T-Clight DSP family, a classic memory-based architecture, with 16-bit or 32-bit word widths and single or dual MACs. The CEVA X DSP family offers a combination of VLIW and SIMD architectures, with different members of the family offering dual or quad 16-bit MACs. The CEVA X CDSP family targets software-defined radio modem designs and leverages a unique combination of VLIW and vector architectures with 32, 16-bit MACs. Analog devices produce the SHARC-based DSP and range in performance from 66 MHz, 198 mFLOPS to 400 MHz, 2400 mFLOPS. Some models support multiple multipliers and ALUs, SIMD instructions and audio processing, specific components and peripherals. The Blackfin family of embedded digital signal processors combine the features of a DSP with those of a general-use processor. As a result, these processors can run simple operating systems like Nuke Linux, Velocity and Nucleus RTOS while operating on real-time data. NXP Semiconductors produce DSPs based on trimedia VLIW technology, optimized for audio and video processing. The trimedia media processors support both fixed-point arithmetic as well as floating-point arithmetic, and have specific instructions to deal with complex filters and entropy coding. CSR produces the Quadro family of SoCs that contain one or more custom imaging DSPs optimized for processing document image data for scanner and copier applications. Most DSPs use fixed-point arithmetic, because in real-world signal processing the additional range provided by floating point is not needed. and there is a large speed benefit and cost benefit due to reduced hardware complexity. Floating-point DSPs may be invaluable in applications where a wide dynamic range is required. Product developers might also use floating-point DSPs to reduce the cost and complexity of software development in exchange for more expensive hardware, since it is generally easier to implement algorithms in floating-point. Generally, DSPs are dedicated integrated circuits. However, DSP functionality can also be produced by using field-programmable gate array chips. Embedded general-purpose RISC processors are becoming increasingly DSP-like in functionality. For example, the ARM Cortex-A8 and the OMA-P3 processors include a Cortex-A8 and C6000 DSP. In communications, a new breed of DSPs offering the fusion of both DSP functions and HW acceleration function is making its way into the mainstream. Such modem processors include ASOCS Modem X and CEVA's XC4000.